Professor Sisir Kanti Mondal is a professor in the Department of Geological Sciences at Jadavpur University, Kolkata. His expertise lies in the petrology and geochemistry of mafic rocks, magmatic ore deposits, and critical mineral exploration. Professor Mondal holds international recognition as a JSPS Invitation Fellow and is a postdoctoral researcher at the American Museum of Natural History, AMNH, New York. He is also a recipient of the BOYSCAST Fellowship from the Department of Science and Technology, India. He has several international collaborative projects to his name, such as the UK UKIERI project with Cardiff University, India-France CEFIPRA project with CNRS-CRPG, and with the CSIRO Australia under the India Australia NPP on exploration of critical metals. He is a sought-after speaker at national and international conferences and serves on editorial boards of leading geoscience journals in the American Geophysical Union, AGU, Society of Economic Geologists, SEG, Geochemical Society, USA, European Association of Geochemistry, EAG, Geological Society of India, Indian Geophysical Union, and the International Association on the Genesis of Ore Deposits. I kindly invite Professor Mondal to deliver his keynote lecture.
Okay. Can you hear me? So, thank you very much, Baba, for your hard work. So, saying so many things, good things actually. So, the title of my presentation, you can see that sustainable resourcing of platinum group elements, studies to understand and locate PG in chromites, chromatites, breccias and magnetites in India. Actually, it was the title of one of my projects under British Council MHRD UKIERI project, India UK collaborative project with Cardiff University, which I had from 2013 to 2016. You can see that it directly related to issues of the sustainability. So it was ahead of time. Nobody recognized our results or nothing. We had discovered PG deposits, but like published those works. So after that, nothing has happened. So this is Nuashahi and this is Shukhinda. This is the current state of Shukhinda. This is the current state of Nuashahi igneous complex. So my project was on like Indian ultramafic mafic rocks, chromite deposits and magnetite deposits. You know that if we have an ultramafic mafic igneous complex at the lower part, we have chromitite ore deposits. At the upper part, within the gabbroic rock, we have magnetite ore bodies. And depending on the time of sulfide saturation in that whole ultramafic complex, we may expect occurrence of platinum group elements at the lower level, say within the pyrrhotite unit. We may expect occurrence of nickel copper sulfide PG at the contact between, say, gabbro and ultramafic rock unit, or we may expect PG and nickel copper sulfide within the magnetite layers. So we have similar kind of, say, ore deposits all over the world. So we know the model. We can apply that kind of model to explore nickel copper sulfide PG in India, because the main reason is that India and Australia, South Africa, all these countries, they are together, part of Gondwanaland. And if you see the metal endowment in South Africa, one of the largest metal producer, you see Australia, they are producing huge amount of metals for the last 100 years. But in case of India, say when British left us, and within the 70 years, we do not have any discovery. So we are looking for metals. So, and we know that we have a climate action to follow. So this ambitious climate action it will bring significant demand for minerals. We need more metals. So there is demand, and if you see the like ambition, so we have to reduce the temperature 1.5 degrees centigrade to 2 degrees centigrade, and it requires like a huge scale of demand for resources, metal resources, and at the same time, so if you do many mining, nasty things are going to happen. Increased mining activities will like destroy the environment and everything. So we have to take care of all other aspects. So the that we need the demand is like 3 billion tons of metals and minerals will be needed by 2050. That is the calculation. And if you see the World Bank paper 2020, you see the escalation actually. So in case of some of the elements like graphite, lithium, and cobalt, so we need more than 450% metal from, if you calculate from 2018 level. So we have a 2 degree scenario, we have 1.5 degree scenario, and they have calculated all these things based on the 17 metals actually. So some of the metals like copper is gold actually. It can be utilized everywhere. So it's a huge demand for copper. Then we have nickel, we have some other elements as well, so cobalt, and in case of, so if you see the demand actually, so it varies. Like in case of India, it would be like 30 or 35 elements. In case of USA, it is more than 50 elements. So in case of Australia, it is 13 or 40 elements. So it depends on the socio-economic condition of the country. So critical or strategic metals are non-fuel mineral or mineral commodity, which are essential to the economic or national security. So this is very important actually, and which are the supply chain vulnerable to disruption. Anytime, like you can see the disruption of supply, and you will be sued. So we have to have our own deposits, and we need to discover more such deposits actually. And there's parallelly, they are taking another program like space programs to extract metals from, say, from meteoritic belt, asteroids. But the thing is that, which is like a too short, so we have only one planet to exploit. So here comes the sustainability issues. Like we have to do green mining, we have to consider circular economy, and the sustainability issues. We have to sustain everything so that we can keep the metals for future utilization. So this is the final set of minerals critical to India. Ministry of Mines 2023, they published this list actually. You see, we have 30 metals which are in demand. Among these, so I did my dissertation on tungsten mineralization in Jadavpur University in 1993. Then my PhD was on nickel, copper, cobalt, PG mineralization, along with chromite, titanium, and vanadium bearing magnetite deposits. So, and all these things are basically related to ultramafic, mafic, magmatism, and all kind of ultramafic, mafic rocks. So these are the commodities I have been working on since my PhD from 1993, 1994, and through postdoc and other projects. So this is related to ultramagmatic processes, which is nothing but we have a source mantle, we need to measure that mantle, we are generating ultramafic magma, that magma is emplaced within the crustal magma chamber due to fractional crystallization along with rock unit due to fluctuation of that magma with respect to ore mineral like chromite or magnetite, or due to sulfur saturation of that crustal magma chamber, or we can expect those things as a superficial processes or as a volcanic system. So those are the extrusive system. That orthomagmatic process has a two end member, one is true high temperature end member where silicate melt crystal equilibrium played the role, and another one is the magmatic hydrothermal process where volatile play important or significant role. So this is classification of ultramafic, mafic igneous rocks. Those are important for ultramagmatic ore deposits or nickel, copper, platinum group element deposits, along with chromite and titanophilus vanadium-bearing magnetite. So this is a book I edited with Dept in 2017. So this particular classification scheme is proposed by Ed Ripley and Tusili. In that book, there is a chapter 3, where you will find this classification scheme. So these are basically flat basalt related deposit, komatiite basalt related deposit, komatiite related deposit, and there are many tectonic settings, intercontinental rifting, backup setting, or subduction setting, where you will find all sort of this kind of deposits. So we have a similar kind of rocks in our country, in our Teton. So we have Deccan, we have komatiites. So we need to explore those materials for this kind of commodities. So these are the occurrences of nickel, copper, platinum group element, chromite, and iron titanium oxide deposits in the world. You can see that North America is dominating, and southern part of African continent, mostly South Africa and Zimbabwe, they have a good deposit. In Brazil, we have something, and in European part, like Scandinavian part, we have deposits. In Russia, we have. In China and Australia, we have deposit. In India, only viable deposits of chromite deposits is in Nuachahi and Shukinda. There's 98% chromite is coming from Nuachahi and Shukinda, mostly from Shukinda actually. And but in Nuachahi we have nickel copper sulfide PG mineralized zone in a breccia zone that we have discovered during my PhD years. Then GSI had a project with BRG in France. They did detailed work on that. So we have known reserves in Nuachahi area. Then during our inquiry project, we discovered PG and nickel copper sulfide in magnetite band in Nuachahi. And then as a follow-up study, we conducted detailed study of prometite from Nuachahi and Shukinda, and also from Nadiali to see if we have some platinum group elements in the prometite itself. So this is the production. You can see that in terms of platinum and palladium, South Africa is dominating actually, along with Russia, and some deposits are coming from, say, United States. So this is the Indian Shield. We have important rock units like ultramafic mafic rocks are in Jadavpur. We have ultramafic mafic rocks in Bandara, also in Sisir Kanti Mondal, and this is our Deccan volcanic province. All these categories are important. The reason is that we have Orphean chromatiites. So if you see the largest chromite, so nickel copper sulfide deposit, nickel copper sulfide along with PGE deposits that is hosted in chromatiite in Kambalda, that is known as Kambalda type nickel copper sulfide deposits, ideal type deposits actually. So those are hosted in chromatiites. And we have plenty of chromatiites in all these patterns. So those are the rocks actually we should explore for nickel copper sulfides. So this is Shingung crater, and Nuachahi is located here, Shukinda is located here, and Mayurvanj. These are plutonic igneous rock, plutonic ultramafic mafic igneous rock, where we have chromite deposits in Nuachahi, we have chromite deposits in Shukinda. At the upper part of Nuachahi, we have magnetite bands or magnetite deposits, and also in Mayurvanj complex, we have magnetite deposits. So this is Nuachahi igneous complex. I did my PhD on Nuachahi igneous complex, and it was like from 1994 to 1997. Most of the analysis I did from this particular institute actually. I used to visit IIT Roorkee, and there was on EPMA lab at USIC, and Professor Manik Basgam was in charge of that particular lab. So there wasn't any EPMA laboratory in India during that time. So it was the only laboratory saved our PhD life. Otherwise, it was very difficult for me to complete that PhD actually. Unfortunately, in that lab, we didn't have any PG standard. So for PG standard, I couldn't analyze my platinum group minerals from here. So but sulfides and chromite and all those olivine octopus and everything has been analyzed. So in the Nuachahi complex, what we have actually, At the lower part, this is the ultramafic unit with 3 chromitite bands. We have Brachia zone, which is sulfide rich and platinum group element rich. Then we have gabbro, and at the upper part of the gabbro, we have magnetite band, and that magnetite band is PGE rich. That is our discovery as well. So this is the cross section of the Noachahi igneous complex and field photograph. This is the dunite unit that hosts 2 chromitite bands. This is our postgraduate final year students. We used to take them over there to show this chromitite as well as some petrological problems are there. So this is the brachia, typical chromitite brachia hosted within pegmatitic gabbro. Those are sulfide rich. And then we have that upper gabbro, and at the upper part of the upper gabbro, we have this magnetite band. Depending on the olivine nodal abundance in chromitite, we have different kind of textural variety of chromitite. And most of the cases, these chromitites are basically, we have massive variety and stratiform variety, but we have net texture. This is a typical igneous texture, cumulate texture. So this is Shukrinda igneous complex. In Shukrinda, we have 2 orthoperic variety in it, but 6 chromitite band. Those are hosted within serpentinized donite unit. The important thing is that in Shukrinda, we do not have any gabbroic part or gabbroic component, but we have a brachia. You know, this saying is from this department actually, Sain and Mohanty, was Amit Kumar Shain actually. So he did, he characterized this brachia zone many years back. So this is the Shukrinda igneous complex and occurrence of chromitite. You can see that chromitite bands are highly weathered, lateritized. So we are running a project now with Australia CSIRO to see that the nickel mobility in laterite as well as platinum group element mobility in laterite. So we, one of our students, she visited CSIRO laboratory and worked on that, and we have some interesting discovery as well. So in any layer intrusion, typical plutonic igneous complex, ultramafic mafic complex, we have seen that say at the lower part we have ultramafic unit or periodic rock, donite periodite rock. Nickel copper sulfide bearing PG bearing horizon may occur within that part, like in main sulfide zone of Reptile Zimbabwe, that is a deposit. Then in Manuscript JM for UG2 chromitite, that occur at the middle level of the igneous intrusion. They are also like famous for PG deposit. Then at the upper part of the igneous complex, this is a differentiated igneous complex. At the upper part of the igneous complex, within the gabbro, we have magnetite band, and for the last 10 or 15 years, people are discovering nickel copper sulfide and PG in this kind of magnetite bands, like in Skagerrak intrusion, in Greenland, in Stella complex in Brazil. So if you see the different rock units in Noachahi complex, what we have actually, we have at the lower part, orthoperoxenite, then danite, it hosts 3 chromitite bands, another orthoperoxenite band is there, then we have PG is brachia zone, then that norite gabbro unit, and that gabbro unit contains a magnetite band. It is palladium rich PG mineralization is there actually, and along with some copper mineral like chalcopyrite and other things. In Shukrinda, we do have that gabbroic part, but within the serpentinite unit or say metamorph or say altered donite unit, we have 6 chromitite bands, and there is a brachia at southwestern part of the igneous complex, but it is similar to the Noachahi igneous complex brachia zone, but the problem is that we have so far nobody has discovered any PG or nickel copper sulfide deposit in that brachia zone. So we have been publishing, like since my PhD years, I have been publishing on Noachahi and Shukrinda and also Nageli and other complexes. These publications are related to PG mineralization in Noachahi area mostly, and I will just summarize the genesis part of the PG deposits of Noachahi at different levels. Like this is the first we have discovered PG in Noachahi Chromitite Gabbro-Brachia zone. This is the map that I did from Fracor area of the Noachahi complex in their underground mining area, which was known as say Bora mine. And these are all photographs taken from underground mines of Odisha Mining Corporation as well as Fracor mines. So the thing is that we have chromitite, broken fragments of chromitite surrounded by pegmatitic gabbro, and the contact part of this chromitite and pegmatitic gabbro, those are basically sulfides. So most of the sulfides are present at the contact part, and those sulfides are platinum group element rich. So there is a certain kind of mechanism that we have to discuss. So this is one of my slides actually. With that slide, I came here in 1994 to analyze platinum group minerals. So I identified this unusual mineral from reflected light microscopy. So more than 50 or 60 grains I discovered during that time under microscope. In India, there is nothing, no place to analyze them actually. So I came here in USIC and discovered that they don't have any standard. So I couldn't analyze them. So I have to wait for another 2 years to publish that paper. So that is a very passionate story of mine. So after 30 hours of journey from Calcutta to IIT Roorkee, then because during that time you have to write your letter. So no emailing, nothing. So you can understand after reaching over here, and Kamal used to tell you that, okay, Shishir, very sorry, we do not have any PG standard to analyze that. So, but you know that these are unusual, and I was very much convinced that these are platinum group minerals because these are unusual. So, my sampling procedure is like that we have a brachia sample, chromitite brachia. You collect sample from here. You collect sample from the contact zone. You collect sample from the pegmatitic gabbro. Do petrography and analyze them. You will find the contrast. Like this is behaving like unaltered chromite or say synchromite or main band chromite, but there is a reaction zone here, and you analyze this part, you will get higher PG. You analyze this part, you will get lower PG. So there is a mechanism actually. So something was there coming up here and interacting with this chromitite, and that was the reason, that melt rock interaction was the reason for sulfide saturation of the magma, and as a result of that, that nickel copper sulfide precipitates, and we have that deposits actually. So Thierry was a BRGM. He became my good friend because he was running a parallel project in Noachahi area. So they characterized everything, like you can see that they had a mechanism. They had everything. So they characterized all the minerals. You can find more than 100 species over there. So this is a nice documentation published in Canadian Mineralogist. So I published my paper in 2001, but just with a couple of analysis of platinum group minerals, but I had bulk of data. So these are the, say, another PhD of that rocks, of those rocks from Noachahi area, done by my first PhD student, Sharifa Khatun, who is a faculty in Presidency University. So this is like at the lower ultramafic unit PG, these are essentially PG depleted. Chromitites, they have some high IPG or indium, osmium, ruthenium PGs, but gabbro is also depleted with respect to PG. But brachia zone, we have PG concentration as I have 26 ppm PG. Like as you take a sample like this, you will find say 26 ppm PG. So anything above 3 ppm is economically viable in our country, in case of PG actually. But the main problem is that we are talking about a brachia zone. So you can hit a sample like this here, then after 500 meters another sample like this. So if you take the average, like average will be coming below 2 ppm or something like that. So that amount of PG is not economically viable. So that is the unfortunate story of Noachahi. So, but if you analyze sulfide-based samples, they will give this kind of palladium fractionated PG, which is very similar to any other deposits in the world. So this was my model from PhD work actually. So here I have said after formation of the ultramafic unit with chromatite bands. At the solidification, there was a deformation event, formation of the breccia zone, that was a tectonic breccia, and through that tectonic breccia, we have that intrusion of that gabbroic magma, which was fluid rich, and due to interaction with the ultramafic breccias, this fluid rich gabbroic magma became sulfide saturated and precipitates that sulfide liquid along with PG actually. And due to that interaction, we have different kind of alteration. And with a follow-up postdoc work in India University with Dept, I have found that from sulfur isotope studies as well as oxygen isotope studies that there was another event which was basically a hydrothermal event, and there was interaction with the seawater, evolved seawater, and that changed the chromite composition, all of that, and mineral composition, like extensive occurrence of chlorite, serpentine, and other hydrous phases are there actually in that breccia zone. So essentially, that deposit was basically magmatic sulfide deposit. Although it was a magmatic sulfide deposit, it was marked by hydrothermal event. So this is the sulfur isotope data, and you can see the value of our Noachahi complex sulfides. It is coming to quantitative value actually, or mantle value. So, and now during the UKIERI project, we discovered this PG in magnetite band. So this is our magnetite band, collected samples from all along this magnetite band, and this is the cross section. This is the road cutting section. Initially, we collected 3 samples, this 43, 44, and 45. We saw that they are giving high PG, like palladium concentration is more than 3 ppm. So I took up extensive field study of these samples of these magnetite bands, mapped it, then analyzed it, and we did petrography and all other things. So we have located 327 platinum group minerals in these assemblies, where most dominating phase is palladium antimonite, and the occurrence of PG bearing phases are very much similar to Noachahi breccia samples. So in terms of like breccia, in breccia zone we have a typical magmatic PG, then we have hydrothermal PG, then we have oxidized PG. In case of magnetite, we have similar kind of occurrence. We have, say, oxides, which are oxidized platinum group minerals. That's the last event actually. We have magmatic platinum group minerals, and we have magmatic hydrothermal platinum group minerals. So these are the normalized PG pattern plot for magnetite with highest PG concentration. These are the lower PG concentration, and all other distribution pattern. Whatever is the case, we can see that we have palladium antimonite is dominating, and in the breccia zone as well, the same thing is happening actually. We have palladium antimonite and bismutho-telluride. Those are the most dominating platinum group, platinum bearing mineral phases. And we proposed a model during that time, published in 2018 in Mineral Depositor. That model says that, like, if you have magma and you remove, say, iron bearing mineral from that magma, say FeO, you are changing FeO activity in that magma, what is going to happen, like, at, say, higher FeO activity? So this is the experiment Dave Busson he did under Tony Nalded many years back. This is a particular oxygen porosity diagram. At that particular level, say we have higher FeO in our magma, the sulfur carrying capability is high. So you reduce the FeO concentration in that particular magma due to removal of, say, ferromagnesium silicate mineral or magnetite from that magma. So you are reducing FeO activity actually. What is going to happen actually? Follow this curve at this point when FeO activity is 5. So your sulfur carrying capability of that magma is reducing as well. So that means the same magma, if you just fractionate iron bearing mineral like magnetite, forming magnetite band, what is going to happen to that magma actually? That residual magma will become sulfide supersaturated, and liquid immiscibility, and all the chalcophyll elements that their tendency is to partitioning into that sulfide liquid. They have like very high order of tendency to partition into sulfide liquid, and that if that sulfide liquid equilibrates with a good amount of gabric magma, so it will scavenge most of the chalcophile elements, they will precipitate, that is the formation of nickel copper sulfide layer or ore deposit, and that ore deposit will be enriched with platinum group elements. So that was the position during that time. That was in 2018, and we are in 2024. So there is another model we are proposing now that will appear in Geosociety of London based on magnetite analysis and petrology of magnetite. We have found something different. So, so we can discuss that later on. But now I'm going to focusing on PG scenario in massive chromitite from Noachahi and Shokinda. So we have collected 21 samples, selected 21 samples, analyzed them. The reason is that they are containing higher platinum group elements concentration, so 500 to 700 ppb, PG in there. So in normalized plot, their character is like that. That means if they show this kind of slope, these are IPG rich. IPG enriched PGE pattern, that means osmium, iridium, ruthenium enriched PGE pattern, which is very common for any chromitite all over the world. But the thing is that most of the cases they are ruthenium rich, osmium or iridium rich, but in our case, these are osmium, iridium, ruthenium rich. And typical PGE deposits, they show this kind of pattern, the palladium fractionated pattern. So these are the association of different platinum bearing minerals in chromatites from Noachahi and Shokinda. We have PGN in chromite, which are altered or oxidized. Then in chromite surrounded by silicates and entirely enclosed in chromite. So these are the alloys we have found. You can see that most of the alloys are osmium, iridium, ruthenium alloys. They are dominating, like osmium dominating alloys actually. So, and we have some other phases as well, like some lawite and oxide, and some oxidized PGs are also concentrated along the veins. We have native ruthenium, native platinum, and also earthite, polymetalite, which is known as arsenosulfide of iridium and rhodium. So there are some differences in PGM occurrences in Noachahi and Shokinda chromitite that you can see here. And one important thing is that we have higher PGE concentration in our chromitite sample. We have many platinum group minerals in that sample. So we have mechanism to identify the tectonic setting from chromite deposit because we are talking about igneous complex. This is a plutonic rock. You cannot just use normal discrimination plots like Pierce diagrams or all these things. You have to model that. You have to find the liquidus composition of the chromite. You can plot them. You can find the tectonic setting. You can calculate the parental magma using modeling. So we did that. I did that thing like during my PhD years. So we have found that in case of Noachahi and Shokinda, the parental magma was boninitic in composition, which is basically a magnesian magma, but hydrous magma, but siliceous magma. So we did I did a osmium isotope project many years back to understand the source character of Noachahi and Shokinda, and I found that these are basically that magma were like extracted from a subcontinental lithospheric mantle-like source. Then I verified that mechanism like using this mineral inclusion study of chromite. We have plenty of minerals inclusions in chromite, where most of the inclusions are chrome dioxide and phloropite. Analyze them by EPMA and the revelation ICP-MS, and they show similarity with the mantle zone is chrome dioxide coming from the lithospheric mantle. So perhaps they are coming from subcontinental lithospheric mantle. So our preliminary alloy study, they show that this kind of model actually. So we had I have 2 minutes. Okay, so I have 1 slide. So this is the depleted mantle and depleted subcontinental lithospheric mantle due to dehydration of the downgoing slab. What is going to happen actually? So it will be metasomatized, and from that metasomated mantle, due to hydrous mantle melting, we'll get a magma. That is our monoetic magma, and that monoetic magma will come up with these IPG alloys actually. So that was our model. So what I am proposing here, actually, that monoetic magma may crystallize alloys at low oxygen porosity condition, or that magma may come up with alloys that were originally present in the mantle. So we have a low melting situation with alloys. We have a little melting situation with alloys, where alloys will not be liberating from the mantle, and we have a high degree of partial melting, like to generate the monoetic magma, we need kind of hydrous mantle melting. It will produce high magnesium magma, siliceous magma, and all the IPG alloys will be liberated from the mantle. So that was a depleted mantle source for Noastahi and Shakila. And the thing is that we have only identified 35 platinum group minerals from chromite out of 21 samples, although we have higher concentration of PG in bulk rock data. So there is a contrast and contradiction. So we try to explain that by identifying, like by analyzing chromite using laser ablation ICP-MS, and we have seen that chromite is basically giving high iridium and osmium and ruthenium signal from their structure. That means that IPGs are basically accommodating in the spinel structure. So that is my conclusion. And these are some of my special issues I edited over the years. I have edited like 7 special issues of different journals, Lithos, Oceology Reviews, and many other journals. We have published a book with Bill Griffin, and we are editing this particular book now. So it will be like already 8 chapters are available online. So, but you have to pay for that. And thank you very much, IIT Roorkee, for giving nice food, and Professor Shaldeep Singh and Rajashri Chakraborty for all the support, and all the research scholars and students, and both of you. Thank you.
Thank you, Professor Mondal, for enlightening us with the national as well as the international presence of these critical minerals. I know I'd love some platinum for myself. So, although we are short of time, can we have maybe 2 or 3 questions? If there are any?
You have?
Yeah, actually, I was looking at the one of the photographs where you have got these breccias, and you are also saying that within the braccia you are having more concentration of PGA.
Yes.
I mean, this is just a wild thinking. Generally, when you have a magma chamber, you get the material from the country. So,
Thank you for asking this question. So to get a PGE deposit, actually, the main requirement is that we have to supersaturate our magma with respect to sulfides. So because, and the problem is that sulfur solubility in ultramafic mapping magma is very low. So, but we have big deposits of nickel copper sulfides from the magma. So what is happening here actually? So we need to change some parameters in our magmatic situation. What is happening actually? Like you can change FU activity, you can change SIRP activity by contaminating the magma. So that will give sulfide saturation and supersaturation of the magma. As a result of that, you may expect formation of a deposit. But the thing is that if you see Kambalda deposit or Norik Stalnak deposit of Russia, those are Norik Stalnak is flat basalt related, Kambalda is komatiite related. So magma is coming up, that plume generated magma coming up, interacting with the say basement rock. So you can change SiO2 activity due to crustal contamination. Magma may supersaturate with respect to sulfides, and we can get a deposit. But to get a big scale deposit, what you need is very simple thing. We have to add sulfur from the outside, sulfur from the sulfur bearing sediments, or you should have a say barite deposit or gypsum deposit. The Gondwana sediments are the ideal candidate for that. Like if you have flat basalt, that flat basalt is coming up, like in Norris, Siberian trap. What is happening over there? We have barite deposit or gypsum deposit over there within the Gondwana sediments. So it is collecting that sulfides, so making itself as a supersaturated magma with respect to sulfides. So liquid immiscibility is happening. So that's why we have that deposit. So in case of Deccan, we have to have that kind of situation, and in that case, we can expect a good deposit.
If you look at the picture which you have shown.
But Brixia has a different type of deposit.
Okay.
So we have similar type of Brixia hosted deposit in large isles in Canada. That is the only other deposit actually, which is also Brixia hosted deposit, and we have a similar situation in Norway and Finland. So we hope that because demand is high, so below 3 ppm value would be usable as well for our country. Maybe not now in 2050. So because research scholars and students are here, so our main duty is that we have to identify whatever we have, and we should keep that for next generation, or we can use that in 2050 or 2075. So that is the main aspect of sustainability. So thank you very much.
Okay.
Yeah, please.
I will not ask what Sandeep Singh asked. Deccan basalt.
No, that is a there. Indians are like Indian they're expecting something. They will go to it. You can have a placard that okay, I am containing a sulfur deposit. Please find it. So that is not going to happen actually. So that mechanism is following by GSI or other exploration companies. All the private explorers, they are expecting that we do the main thing, university people, we will do the prospecting, they will do the discovery and tons of awards and other things. But the thing is that it has a science. You know your rock, do petrology, do geochemistry. First requirement is that you have to identify that crustal contamination. Second requirement is that whether we have external sulfur in that system or not. If you do not find any crustal contamination in your magma, in your Deccan basalt, just leave it. If you do not find any sulfur, say external sulfur in your system, there is no meaning actually.
Professor, but one of Deccan basalt research group, they were talking about the crystal contamination when the basaltic.
But that is not new. Like if you go through Frederick Frey's Deccan paper or any Deccan paper, you just take out those niobium and tantalum ratios, you will find that Deccan is a flat basalt. Continental flat basalt are crustally contaminated. Historically, they are proved. Everybody knows that. It is our if people are saying that okay, we have found crustal contamination in Deccan basalt. What is the point of that? What is the point of that? If you are an igneous petrologist and you have magma, it is penetrating through continent, it should be crustally contaminated. So Deccan is crustally contaminated. Everybody knows that. But the thing is that you analyze Deccan polytic basalt, say 16 to 17% FeO concentration. So that is the right kind of iron concentration is there, titanium concentration is there, crustal contamination is there. We do not have any sulfide liquid immiscibility in that rock. So that is the problem. The reason is that that particular flow, it has never made any sulfur bearing horizon during its journey. That is the reason that we do not have that deposit over there. But I have samples from Deccan, they are containing sulfides. So I have that sulfide bearing samples from Deccan.
Let us see that.
Yeah, but so I need like good passionate worker for that like me, so that they can work on it. So like I have been waiting for last 3 years to find a good student who knows how to clean his table actually, how to clean his books, how to clean his microscope. So until that part is over, there is no point of doing PhD already.
Thank you, Professor Mondal. We'll be moving on with the time constraints.
We now resume our speed talks. Let me introduce the session chairs for our